Hello everyone, let us see next chapter. The name of the chapter is the functions of complex variables. Okay, this is the fifth chapter we are going to see now. Let us see first some basic things. The complex number. The complex number can be represented in the form of z is equal to x plus iy, where I value is the basic complex number, that is I is equal to root of minus 1 or I square is equal to minus 1. And x and y, these two numbers are real numbers. Then such number z is equal to x plus iy is called as a complex number. Okay, this we know. Where x is called, this function or this real number is called a real part of z, and y is called imaginary part of this complex number z, because y is attached to the basic complex number I. That's why it is called as imaginary number, and x is called as real number because it is not attached to I. Okay, now this complex number can be represented by the point pxy, where x is this number and y is the number attached to I, with positive negative sign whatever it is present in the given number. And it can be represented as in the arrogant diagram. Okay, the point is in the xy plane. Okay, this is the complex number z is equal to x plus iy. X is called, this is real part of z, y is called the imaginary part of z, and it can be represented, this point complex number can be represented graphically in the form of this graph, and this graph or this representation of any complex number is called as a arrogant diagram of a complex number z. Okay, now this is xy plane. Suppose this is origin, this is x. Okay, suppose this is o a. Okay, this is point, suppose a, and this is the point p. Okay, and x is pxy, this is the order pair in the xy plane. This is xy plane. Suppose this is the perpendicular, this is the perpendicular line, this we know. This distance is obviously y. This distance from on x-axis is the distance x. OA distance is x. Suppose this is a hypotenuse, suppose this distance is r, and suppose this is theta, the angle PO or AOP is theta. Then by the Pythagoras we know r square is equal to x square plus y square. Okay, that's why r is equal to root of, taking root on both sides we get root of r x square plus r square. Okay, this is the basic concept of complex number. Okay, the representation of a complex number and the arrogant diagram or a representation of complex number in xy plane. This is called arrogant diagram of complex number. Okay, now conjugate of complex number. Suppose z is x plus iy be any complex number, then conjugate of this complex number can be denoted by z bar, and it is defined as, just replace the middle sign. If it is plus, take it minus. If it is minus, take it plus. This is called the complex conjugate number of this number z. Okay, for example, suppose z is equal to 3 plus 2i is the one complex number, then its conjugate is, just replace this plus by minus sign, that is 3 minus 2i. If suppose z is equal to minus 1 minus I, then we have to just replace the middle sign. Okay, that's why the complex conjugate of this number becomes minus 1 plus I. Okay, now modulus of z. Next term is modulus of z is defined as, suppose z is equal to x plus iy, this is one complex number, then modulus of z or mod of z can be defined as, can be denoted as, first mod of this z, the two bars, and is equal to under root of x square plus y square. This number square, whatever it is plus or minus sign, negative number square is always positive, that's why in under the square root sign doesn't matter, that's why this number square plus this number square, and this we know it is r. Okay, that's why this r is called the modulus of or mod of this complex number z. Taking square on both sides, we get mod of z square is equal to r square is equal to square and square root get cancelled, x square plus y square. This is a modulus of z. Now properties of complex number, let us see. First, mod of z and mod of z bar are same. Okay, if you find out z bar is complex conjugate, if we calculate modulus of z and modulus of z bar, both are same. Okay, that is x square plus under root of x square plus y square. Now z into z bar is equal to mod of z bar. How it is, let us see. Z into z bar is equal to x plus iy into mod z bar means x minus iy, complex conjugate. Multiplication of t, these two brackets, first multi x, a plus b into a minus b is a square minus b square, formula is there. Now x square minus I y square, that is I square y square. We know I square value is, I square is a complex, basic complex number whose value is I square is minus 1. That's why I put value here. I square is equal to minus 1. We get x square minus minus plus y square. And what is this? This is a mod of z square. Okay, taking square on both sides. That's why z into z bar is equal to mod of z square. Okay. Let z is any complex number and C denotes set of all complex numbers. Then function defined as f of z, that is f from s, that is s to s is a domain set and it belongs to C. C is a set of complex numbers. Then s is called a domain of the function f of z or f, and f is called a complex function because its codomain is set of complex number. Okay, that's why it is this function f of z, where z is a complex number, that's why it is called function f is called complex function. For example, f of z is equal to z square. Okay, it is different than f of x is equal to x square because that x is a real number, and while here f of z is z square, z is a complex number where z value is x plus iy. Okay, that's why it is called a complex function. Suppose let f of z is equal to u plus iv, which is equal to w. In the throughout the chapter we denote w as u plus iv and z is equal to x plus iy. If corresponding to each value of z there exists one and only value of w is equal to f of z, then w is called single valued function of this z. Otherwise it is called multi-valued function of z. Okay, these are some definitions. Now, limit of f of z. We have to find out the limit of function f of z. The number L, small l, is called limit of f of z as z approaches to z naught if for every epsilon greater than 0 there exists delta greater than 0 such that modulus value of f of z, this function minus this L mod complete, is less than epsilon. For every mod of z minus z naught, difference between these 2 points should be less than delta. Okay, if it is there, then this L is called limit of this function f of z, and it is denoted as limit of z tends to z naught of f of z is equal to small l. This is similar to the normal limit definition. Okay, just the only difference is z is a complex number here. Okay, now continuity of f of z. Function f of z is said to be continuous at particular point z naught if there are three conditions for f of z to be continuous at a particular point z naught. What are those conditions? Let us see. If f of z naught exists, first condition, comma, limit of f of z as z tends to z naught should be exist, and third condition, these two must be same. Limit of z tends to z naught f of z is equal to f of z naught. Okay, this must be same. Now, if any one of the above condition fails, if among these three conditions, if suppose any one of the condition fails regarding to particular one function f of z, then that particular function is said to be obviously discontinuous. Okay. Now there are some notes are there. If f of z and g of z are two continuous functions, then their addition f of z plus g of z, their subtraction f of z minus g of z, their multiplication and their division are also continuous functions. Okay, where z is obviously complex number. Second note, if f of z is equal to u plus iv is a continuous function, then both u and v are continuous. Okay, if such function f of z is continuous, then on RHS side u and v also continuous functions. Okay, now next definition, derivative of f of z means f dash of z. Let us see the derivative definition of a complex function f of z. If w is equal to f of z, suppose w is equal to f of z is a single valued function of z, where z is x plus iy point, then derivative of f of z, that is differentiation of f of z, is defined as, this is a definition, dw upon dz, like dy by dx, dw by dz, derivative of w with respect to z is equal to f dash z. W is nothing but f of z, and its derivative is f dash z with respect to z is defined as limit as delta z tends to 0, f of z plus delta z minus f of z divided by this delta z. This is similar to normal derivative definition. Okay, let us see next, analytical. This is a very important point. We have to solve so many examples, depend on the main basic syllabus start from here. The rest of the earlier information is are just basic things. Okay, now analytical function or analytic function. A single valued function f of z is called analytic function if f of z possesses a unique derivative at every point of the given region R. Okay, analytic function is also called a regular function or holomorphic function. If suppose in any example these are the synonyms to the analytic function or regular function, or they can ask for holomorphic function. Three of them are same. Okay, this is the basic definition of analytic function. A point where function is not analytic is called singular point. Okay, there are some loopholes regarding this analytic function. Those loopholes means those points where function is not analytic. Such points are called singular points or singular point. For example, f of z is equal to e raised to z sin z cos hyperbolic z are the analytic function or analytical function. This is the basic theoretical definition. Now let us see the definition or the necessary and sufficient condition which we are going to use in the particular examples. Okay, necessary and sufficient condition for fz to be analytic. Let f of z is equal to u plus iv, which is obviously w, remember this, where u and v are functions of x and y, where u and v are not numbers, they are functions of x and y. Then necessary and sufficient condition for fz to be analytic are, there are two conditions. First one, w by w x, w by w x means, or dou u by dou x means derivative. These are the partial derivative. Okay, partial derivative in the sense while taking derivative with respect to x, you have to keep other variables constant. Like for example, if you are taking derivative of u with respect to x, y is constant. If you are taking derivative of u with respect to y, obviously x will be constant. At that those are partial derivatives. Okay, the first condition is w by w x, w by w y, w v by w x, w v by w y. U derivatives of u with respect to x and y, derivatives of v with respect to x and y are continuous function. First condition. And second most important condition is w by w x must be equal to w v by w y. That is, this derivative is equal to this derivative, and this derivative w by w y is equal to minus w v by w x. These two equations are called Cauchy-Riemann equations, or they are called in short CR equations. Okay, whenever there is a question regarding analytic function, we are going to use this condition, CR equations, okay, while solving the examples. W by w x is equal to w v by w y, and w by w y is equal to minus w v by w x. Okay, remember, this is very important. Now this is the Cauchy-Riemann equations or CR equations in obviously Cartesian form. What are the Cartesian and polar form? Cartesian form is nothing but where x and y variables are there, and the polar form are consisting of r and theta variables. Okay, these are the most visible difference between those two forms. Okay, spaces. Now Cauchy-Riemann equations, that are CR equations in polar form. Let us see. Let r theta be the polar coordinates. Okay, x and y are Cartesian coordinates, r and theta be the polar coordinates. Then we know x is equal to r cos theta and y is equal to r sin theta. How we calculate those equations? From this. Okay, what is if you calculate from this, what is sin theta? From this, the opposite side upon hypotenuse, that is y upon r. Okay, from this y is equal to r sin theta. Okay, what is cos of angle with cos of this angle? Adjacent side upon hypotenuse, that is x upon r, which implies x is equal to r, take r on that side, cos theta. Okay, these equations are called basic relationship, basic equation, which represent the relationship between Cartesian coordinate and polar coordinates. In these two equations, all coordinates are present. X and y is also there, r and theta is also there. That's why this is a basic relationship equation between Cartesian coordinate and polar coordinate. X is equal to r cos theta and y is equal to r sin theta. Okay, now therefore z is equal to convert this Cartesian form into polar form, we get z is equal to x plus iy, basic point, which is equal to, put x is equal to r cos theta here, plus I as it is, y is equal to r sin theta. Take r common, we get cos theta plus I sin theta, and we know value of cos theta plus I sin theta is nothing but e raised to I theta. This is a basic definition of exponential. E raised to I theta is cos theta plus I sin theta, where theta is this angle. Okay, therefore this is the exponential form, this is polar form, and this is Cartesian form. These are the three forms. Now polar CR equations in polar form are this: w by w theta is nothing but is equal to minus r w v by w r, comma, w by w r is equal to 1 upon r w v by w theta. These two equations you have to mug up. Okay, now here is some note. CR equations, you can these two equations you can mug up like this short form, where ux means derivative of u with respect to x, that is w by w x. Vy means derivative of v with respect to y, w v by w y, like this. Ux is equal to vy, uy is equal to minus vx is the Cartesian form, and these are the polar forms. U theta is equal to minus r VR, and u r is equal to derivative of u with respect to r, that is 1 upon r v theta. Okay, just mug up these 4 equations. These are called polar CR equations, Cauchy-Riemann equations in polar and Cartesian form. Next definition is harmonic function definition. Any solution of the Laplace equation del square phi by del x square plus del square phi by del y square. What is del square means? Second derivative of phi, double derivative of this function phi. Phi is any function of x and y. If phi satisfies this equation, this is the equation called Laplace equation. Then any solution means finding out what is the solution of this differential equation. The finding a value of the phi, value of function phi, and such phi is called harmonic function. Okay, thus real and imaginary part of the analytical function f of z satisfies the Laplace equation. Hence, that means if any function f of z is analytic, then it must satisfies the Laplace equation. That means u and v, real and imaginary part of f of z means u, hence u and v are known as a harmonic function. Okay, what is our f of z? U plus iv. Okay, that is equal to w. If fz is analytic, then u and v must be harmonic functions. Okay, next, orthogonal system. Suppose two families of curve, these are the two equations of two curves u and v. U are function of x and y, v is also function of x and y. Uxy is equal to c1, c1 is a constant, c2 is also constant, vxy is equal to c2. These are the two equations of two curves. Okay, then are defined two families of curve. These two forms are defined by the analytic function f of z, we know it is u plus iv, are forms an orthogonal system. What do you mean by that? If f of z is equal to u plus iv is an analytical function, then u and v are, these two curves are orthogonal to each other. Orthogonal means the orthogonal lines means the lines which cut each other or intersect each other at 90 degree. Those lines are called orthogonal lines. Likewise, orthogonal system means a orthogonal system of curves. Two curves, like for example, suppose this is one curve, this is other curve. Okay, this curve intersect at this point, and draw the tangent at this curve, draw other tangent to this curve. Okay, at the same point, and if it is suppose this angle is 90 degree, then these two curves are called orthogonal curves or orthogonal system of curves. Okay, now what is our statement? F of z is an analytical function u plus iv. F of z is equal to u plus iv. Then u and v are defined like this, are orthogonal to each other, are forms orthogonal system. Let us prove this statement. Proof. Now, differentiating one, you can ask this theoretical. This is a theoretical question. Okay, they can ask prove that f of z u plus iv is equal to u plus iv, which is an analytical function, forms orthogonal system. You have to give this proof. Now let us start the proof. Differentiate equation 1 with respect to x. Okay, now you have to use differentiation or every rule of differentiation, that is chain rule. U is a function of both x and y. Now we have to differentiate the given function with respect to x on both the side, LHS and RHS, where y is a function of x and x is a now independent variable. That's why first it is addition of both the derivatives. First del u by del x, okay, plus del u by del y into y derivative should be multiplied, that is dy by dx. This is the basic definition of chain rule of derivative, is equal to derivative of c1, that is derivative of constant is 0. Okay, remember this step. Derivative of 1, differentiating equation 1 with respect to x, we get del u by del x Here you don't no need to write a bracket x and y. Okay, this is a self understood term, that is u and v are functions of x and y. W by w x plus w by w y into dy by this y dy by dx is equal to 0. Okay, implies, now calculate dy by dx. From this we get dy by dx is equal to, what do you mean by we know two lines, we are going to use one theory here. If suppose this is one line, okay, this is other line, okay, suppose this line's slope is m1 and this line's slope is m2, and suppose these two lines are intersecting each other at 90 degree, then we know one theorem, that is a multiplication of these two slopes of two lines where two lines are intersecting each other at 90 degree is -1. Okay, this theory we are going to use here to prove this statement. Therefore, we have to find out dy by dx from this equation first. Dy by dx is equal to, that is m1. For suppose this is the first curve, that's why we are denoting m1 as slope of the first curve. Slope of the first curve uxy, which is equal to, take dy by dx, take on this side, this term on that side, and this should be divided to that time. It must be minus w by x upon this w by y. Okay, taking terms on that side only. This is slope of first curve. Now we have to find out slope of other curve. That's why in the similar manner. That's why in the similar manner, differentiate equation 2 with respect to x. What we get? Same way, just replace u by v everywhere, and from that we get, of course we have to find out slope of other curve, that is dy by dx from here is equal to m2, call it as m2 is equal to slope of second curve vxy, okay, is equal to c1, we can write as it is equal to, take dv by dx on that side and dv by dy on denominator, we get minus dv by dx upon dv and dv by dy. Okay, these are two slopes we just found of these two curves. Now what we have to show, product of these two curves must be -1. Now let us see the product. Consider m1 into m2, that is multiplication of these two. Okay, minus minus gets plus, and above, okay, now these two minus sign gets cancelled. Now w see, fz is an analytical function. Given thing fz is an analytic function, that's why fz must satisfy the CR equations in Cartesian form. That's why, what is the CR equation in Cartesian form? Ux is equal to vy, uy is equal to minus evx. These are the CR equations. Use these CR equations here. You replace here w by x by vy, that is w by y, and w, this is w by y on this side, w by y as minus vx, that is minus w by x, and cancel out this with this with this, we get answer -1. Okay, that's why product of these two slopes of these two curves is -1. That's why these two curves are orthogonal to each other. This is the proof. Let us see note. First note, if z is equal to u plus iv, then z is equal to x plus iy. Remember this. Second, e raised to I theta, value is cos theta plus I sin theta. And similarly, e raised to minus I theta means just replace plus by minus sign here. Everything is same. Now, sin hyperbolic z is e raised to z minus e raised to minus z upon 2. Cos hyperbolic z, hyperbolic definitions are there. E raised to z, cos, for cos it is plus, for sin it is minus, e raised to minus z upon 2. These are the basic hyperbolic definition. Now, dash means derivative. Okay, in normal trigonometry, sin derivative is cos and cos derivative is minus sin. While in the hyperbolic function there is no plus and minus sign. Sin hyperbolic x derivative is cos hyperbolic x. Cos hyperbolic x dash means derivative is sin hyperbolic x. Remember this. Rest of the derivative rules, all the chain rules are same. Now let us see the first example.